Hi everyone, Mr. Ford here again. We're going to finish worksheet 5A that we didn't get to last time. We're going to finalize some things with refraction, which was the bending of light as it goes from one medium to another, and it bends because the wave or the speed of that wave will slow down or speed up. So before we get through the ones that you see on the screen now, we're going to go to a PhET simulation. So there is a PhET simulation linked in Schoology for you to look at. And it's basically here we have, I have to set it back to original settings. So we have a laser, right? You can turn the laser on. We have our two surfaces, our two materials, air and water, you can see on the right hand side. And the only thing we're going to really use is this protractor. You can drag and drop it, trying to line it up the best that you can with the boundary of our surfaces and our normal line. Close enough. So we could turn on our laser pointer, we can move it around, and we see that some of the light bounces off, meaning it stays in the air, it reflects, and some of it goes in. So the lighter line at the top of the screen, that is the light from the laser that reflected. Now you notice it is lighter. That just has to do with our surface. Some of the light is bouncing off, yet some of the light is going through. So something that we already showed that if it was in school lab, we could have a mirror or some reflective surface and prove the law of reflection, that incoming light ray would be equal to the one that is reflected. So those angles relative to the normal, or you could think of between this boundary of the surfaces, are going to be equal. So there's our proof that that does exist. What we're focusing on today isn't the light that bounces off, but the light that goes through. So in a lab, in class, what we would have done is I would have given you some different ways to look at an object through a piece of clear plastic, and we could change those angles and see how the light bent. So we could see that as it goes through, our angle, let's do it like this. So our angle of incidence is 30 degrees. We're looking at the top of the screen. I don't think I could write on this. So between the top of the protractor, 0 and 30, that is our angle of incidence, our incoming ray. Now the angle on the bottom within the water, the blue area, that's not our angle of reflection, but in this case, angle of refraction. So again, it is measured to the normal line, and that is approximately, so this would be 30. So that's about 20 degrees, give or take. Maybe we call it like 20. So if this is exactly 30 going in, coming out the bottom, maybe 31. So we see the light that does bend. So what we could do is change these angles and see how that affected the refracted light ray angle-wise, and did some analysis with some charts and some math and gotten some numbers. So in this, we are given the index of refraction of 1 and the index of refraction of 1.33. Now, an index is basically a comparison. It's a number. So thinking back to last class, light will, or waves will refract, meaning bend as they go into new mediums, because they will speed down or speed up or slow down. So everything is comparable to air, because that's what we're going to be most of the time be looking at things in, right, on Earth. So our first index, our comparison, is 1. So if we see air going from air to air, it's not going to change. So that is our level of 1, the speed of light in air. So when we go to the speed of light in, say, water, it's kind of a factor. So it's going to be 1.33 times slower. The light is going to slow down, and that's what's going to cause it to bend more towards our normal line, or in this picture, downward. So just by moving this index of refraction, right, so air to air goes straight through, as we increase the refractive index, or basically how much the light slows down by, it bends more and more and more away from a straight line. So it's going more and more towards that normal line. So it's something we didn't define last time. It's a kind of a relative comparison or a ratio of the speeds of light, which instead of dealing with these huge numbers, we ratio it down to compare it to the speed of light in air. So what we can do is go back to our notes here, and I'm going to go down a little bit. So here we go. So we're going to talk about something called Snell's law, which is essentially, like we said, a comparison or mathematical model for how much light is going to bend, or how much waves are going to bend as they enter a new medium. So what we're going to look at is an N. So this is our index of refraction, and that's what N represents. I is our incident, or our incoming light ray, or medium. And we're going to take that and times the sine of that incident ray. Now we use sine just because that's a better representation of like the hypotenuse, because that's what we're looking at as far as our triangle goes of that incoming light ray. And we're going to set that up as the refracted index of refraction, or the speed, right? If we really wanted to, we could call it, our actual speeds of light coming in, or our waves, but we're not going to get that detailed in it since we are not in a live class. So this is Snell's law. Really easy math as long as you can find your sine button on your calculator and how to do inverse sine. And this is essentially, if we rearranged it, comparing the relative speeds with the angles that the light is going to be bending at. So really easy kind of lesson, knowing that just Snell's law. You would be given this on our test or quiz in class, or hey, on Schoology. So going back to our, we didn't have to go back anywhere. Page 2 of worksheet 4A, and we have some problems. So here we have light coming in at 40 degrees, and keep in mind this is relative to our normal line here. This is our incident or incoming light ray. We do have our index or indices of refraction. We can see that 1.3, the light is going to travel faster in water than in glass. And we're just going to use Snell's law to predict which way it's going to go. So we kind of already know which way. So this would be straight through, say. So we already learned that since the light or the wave is going to slow down, it's going to bend more towards the normal line, right? When it goes from slow to fast, it goes towards a normal line. If it was the reverse, it would bend upward. So using our Snell's law, we can say our 1.3 sine of 40 degrees. And this is why it's good to have that, or use that angle that is our true index, or I'm sorry, incident angle of incidence. Our glass index of refraction, and we're going to figure out what the refracted light ray would be. So we just plug that into our calculator, and we get an index of refraction of about 30, we'll call it 34 degrees. So in class we could measure this out, but we do know that it's going to be a little bit less than straight, because if this is perfectly straight, that angle is 40 degrees, so it's be a little bit less. We can exaggerate it a little bit and show that this is our 34 degrees here. We're going to skip the number 7 below just because it was a similar problem. Air going into glass. So yeah, it's still going to bend towards that normal line. Our index of refraction in air is 1, so it's going to be 1 times sine of, this is the tricky part, we need our incoming light ray. So this is going to be 90 minus 36. Good job, 54 degrees. That's going to be equal to 1.5. Again, we're using that Snell's law equation. and we're solving for our missing angle. So we plug that into our calculator, and that hopefully should spit out, let's see, what is it going to be? About 32.6. We'll call that 33. And again, depending upon how your calculator works, you may have to hit like your second sine button because we're finding like the inverse sine, or we're solving for the angle that's within sine. So this being straight, now it's straight, so that would be 54 degrees. So we're going to be a lot less. And this would be our 33 degrees, give or take. 6 is an interesting problem. This will really test your geometry skills. So if we have our 2 index of refractions, it's going from water to glass. So good question. Would it bend? No, it would not bend. The light is only going to bend or refract when it approaches a boundary at an angle. So even though these are 2 different densities, or the light is going to slow down, it's still going to go straight through. Now what we're looking at is it for it bending when it comes out of this triangle or prism. So if that's our normal line, the problem comes, we don't have any angles, but we do know that it is a 45, 45, 90 triangle. So we know this is 90, and this still was 45, so that must mean this is 45. So if our angle of incidence right here is on the other side of this 90, right, because our normal line has to be 90 degrees, this is also 45 degrees. So a little bit more thinking involved for this one, but nothing new that you haven't learned before, probably a few years ago in geometry. So the light is going to come here, and it is slowing, it's going to speed up, sorry. So if this is straight through, would it go away from the normal line or towards? All right, so it's going from glass, which is 1.5, to water, which is 1.3. So it's going to speed up, so it's going to go away from. Now exactly we don't know yet, so that's where Snell's law comes into play. So we're in the glass, so that's going to be 1.5 sine 45 degrees. Going into the water, 1.3. We're right here. And we're looking for that missing angle, not Q. And that's our refracted angle. So we solve for that, and we would get about 54.7 degrees, which straight this would be like 45. So we're looking to make that angle between the normal line and the line that I have drawn bigger. So it goes away, and this would be our 54.7 degrees. Cool. And the last one, number 8, nothing really given to us. We could do this straight up with an equation. I'm a little bit more visual, so I want to draw my light rays here. So the light coming in, here's my normal line. This angle is going to be 25 degrees. This N is going to be 1 because it's air. This N is going to be, this is what we're looking for. This is the plastic, and we're trying to find the index of refraction. And just like mu's, right, coefficients of friction, the only real way to calculate coefficients of friction is experimentally, because it may be off a little bit. Each piece of plastic or wood or what have you is going to be different. Same thing with glass, air. Air can be different densities, temperatures, humidity levels. So that's going to change the way light will travel through it. But there are tables out there that would give you an average of general conditions for, or general N values. So back to our problem. Plug everything into Snell's law, 1 sine of 25 degrees. And N of a refracted one sine 21 degrees. Plug that into a calculator, and we would get an n of 1.2. The one thing I didn't draw on here was my 21 degrees, which wasn't that essential, but we would get this 1.2. So where that you might see this in everyday life, with if you wear glasses or contacts, if you swim or have any kind of goggles on, right? If you've ever noticed, if you go underwater and you open your eyes, you cannot see clearly. That's because your lenses in your eye and the way we perceive light and vision is based upon seeing in air. So if you go under the water and open your eyes, you still see things, but it's not clear because we are not used, our lenses in our eye isn't shaped so that we can comprehend that change in medium, that change in index of refraction and light bending. Number 9, again, just more practice with Snell's law. We have a light source under the water and we are looking at it or looking at something under the water. So the light is coming from the water out into the air. So let's see here. Straight up, just some math. You can feel free to draw in things if you like, but we're going to use Snell's law with our index of refraction of our water, right? Because we're starting in the water. And that angle with the water is 35. So we're looking at, say, this angle there. And it's going into air, which has an index of refraction of 1. And we're finding this angle here. Simply plug that in. Calculator spits it out. And we get about 4950 degrees. C. Now suppose the that's supposed to be incident. Okay, incident angle, incidence angle is 80 degrees from the normal. What's going to happen now? So we're doing the same problem, but just changing the angle. And so I want you to go ahead and plug that into your calculator, and I want you to see what it says. I'll give you a minute to do that. Okay, so what it is telling you is that there's an error. The reasoning is that the light is not going to bend more than 90 degrees, right? It's not going to completely reverse directions. And this is weird. So going back to our PhET simulation, I'm going to change a couple things because we can't move the laser underneath. So let's say we have, this is kind of like the problem, it's just kind of flip-flopped. At the top in the blue, that's our water, and the light is coming from below. You'll notice right here, none of it goes into the air. Right? All of the light is reflected, meaning bounced off, within that medium. Once I come up to about here, some of it starts to now escape. Right? So what this angle is, right there, that kind of boundary there, it's right around, I don't know, 48 degrees or so, right? That's known as the critical angle. So depending upon the angle that the light is coming in at, depending upon the refractive properties or the index of refraction of the two mediums, there's going to be an angle where the light will not be able to go through. This is kind of like skipping a rock in a lake or a pond. So if you threw a rock straight down, it's of course going to go straight into the water. And as you increase that angle from the normal line or decrease the angle that you throw with the horizontal, increases your chance of skipping that rock. There's going to be that critical angle with, of course, the speed that you throw it, the shape of the rock come into play, but there's going to be that magic or critical angle that allows you to skip that rock. Anything above it, depending upon how you look at the angle, but anything too big or too small will or will not skip. So That's what's happening here. So if you ever have a question like C, that's saying, oh, that angle of 80 degrees is above the critical angle, so you would not have any refraction. It would be all reflection. Now the cool thing that, or the interesting thing about this is how fiber optic cables work. So once light gets within a fiber optic cable, the properties of it, how it is bent, how the connectors work, and the index of refraction, light will not escape it. It will continually bounce within it when you bend it. So that's the main principle that drives fiber optic cables. So how would we find this critical angle? So it's still Snell's law. So we're looking for this angle. And we want to know, when it goes out into the air, our boundary is going to be 90 degrees. It's not going to go more than 90 degrees. And that's going to be, if you do sine 90, it's going to give you 1. So when we plug that in, our critical angle here is about 49 degrees, which is what we kind of saw in that FET simulation. That's a little bit harder because it's not perfect and some of it's bouncing off, some of it's going through. But that's how you would find that magic angle. All right, so that's it as far as packet work for today. What you're going to do next is there's 2 interesting Edpuzzle videos for you to watch. Just things that I thought were cool. One is about reflections on curved mirrors, essentially a spoon, and the other is about sunblock, which I thought was kind of interesting. So a little bit lighter of a day, so feel free to catch up on some work that you haven't done. Enjoy nice weather. I believe the day that you're doing this is supposed to be nice. Maybe study or take a AP exam, and you'll have some more work next Blue Day.